common ion effect. So if I say the common ion effect, so before we start this chapter, let's define the definitions. So if we say the depression or decrease in dissociation of weak electrolyte with the presence of strong electrolytes having both common ions. So like depressions or decrease in dissociation of weak electrolytes. So decrease in dissociation of weak electrolyte with the presence of strong electrolytes having common ions in between them. So let's say like if you have the CH3COH, this is weak acid, so this is weak electrolytes, and with that if you add any strong electrolytes, CH3CO and this is strong electrolytes, and that in between the weak electrolyte and strong electrolyte they should have one common ions. Any weak electrolyte, any strong electrolytes, if they have the common ions, then there will be one effect came, that is common ion effect, that is the dissociations of weak electrolytes will decreases. So that's what common ion effects. So if here common ion is CH3CO minus, this is common for both, like if CH3COH or this is dissociated into CH3CO minus plus H plus, and CH3CONA, this is the strong electrolyte, so it dissociate Na plus. So in between CH3COH and CH3CO minus, these both are common ions. So if you in solutions, if you have weak electrolyte and strong electrolytes, and if they have the common ions in between them, then the effect will comes, that is common ion effects. Any electrolytes, if they have strong and weak and the common ions is present in between them, then this effect will come. So this is called common ion effects. So for like if you say what are the weak electrolytes and what are strong electrolytes, so if you talk about of strong electrolytes, so strong electrolytes are generally like if so in electrolytes, what I say, in electrolytes we have cations part and anion parts. Electrolytes, cations and anions are present. Like if we say CH3COH or if we say NaOH, strong electrolyte. So any electrolytes, there have two parts, one is anions and another is cations, another is anions. So here the two parts are what, CH3CO minus and H plus. Here also two parts are there, Na plus and OH minus. So this is the anion parts, this is cation parts, this is cation part, the anion parts. So any electrolytes, they have the two parts. So any electrolytes have any electrolyte have two parts. One is anion part, another is cation part. And if if either anion part is strong and this is weak, then also this is considered as strong electrolytes. Anyone, like if this is weak and this is strong, then also it is this is electrolytes, then also it is considered as strong. And if both are strong, anion part is strong and cation part is also strong, then also it is considered as strong electrolytes. And if both anion parts is weak and cation part is also weak, then it is considered as weak electrolytes. So sorry, so if anyone is strong, either canions or cations, anyone which is strong, then that is called as strong electrolytes. Here is strong, so this is strong electrolytes. Here both are strong, that's why it is strong electrolytes. And if both are weak, then it is considered as weak electrolytes. Okay, so you understand that what is strong electrolyte, what is weak electrolytes. So in common ion effects, if we have the electrolytes, weak electrolytes and strong electrolytes in the solutions, and if they have any common ions in between them, then the common ion effect will come. So common ion effect means decrease in the dissociations of weak electrolytes. Okay, so let's take how it is decreasing its dissociations value. So let's say if I write HCl, or let's say HCN or anything, you can let's say HCN. This is weak electrolytes because this H, it comes from acids, that is CH3COH. So this H came from weak acids, so this is weak, and CN is also from weak base, so this is weak acids because both components are weak, so this is comes from weak electrolytes. Okay, or we can take NH4 NH4, which one, NH4 plus, this is also comes from weak, and NH4CN, this one also you can take. So let's take CH3COH. Okay, so here, sorry, CH3COH, this is weak electrolytes because both CH3CO minus, or which I'll take. So any weak electrolytes you can take. So weak electrolyte means like here we are taking about of the salt, right? So this is comes from onions and wicks and which, so we are talking about of salt. So I take any weak electrolytes. It may be salt or it may not be salt. If you simply take weak acid, then also it's fine. If I take salt, then both will come. This is only for salt cases. Okay, so either it may be salt or a simply weak acid is present, then also fine. Like if you take the for salt cases, then like to take HCN. So here this H comes from weak acid and Cn minus comes from one weak base. So if you dissociate it, then this is since weak acid, so this is weak electrolyte, so this is partial dissociate. that will be H plus Cn minus. Okay, and if we have the NaCl, so this NH come from NaOH, so this is any one will become strong, then that becomes strong electrolyte, so it will dissociate, completely dissociate into Na plus OH minus. So you understand that when we give the both error, that means weak, and if you are giving the one error, means this is completely dissociate, and that is generally weak, so that we represent for weak as strong electrolytes. So here what, sorry, Cn minus, so here that Cn minus is common for both the electrolytes. So this is weak electrolytes, this is strong electrolytes. So for strong electrolytes and weak electrolytes, the common ion is Cn minus. So what happened here, like if we say that let HCN is dissociate into H plus Cn minus, let's initially it is having C concentration 0, now when T equal to 0, when reaction not happened, so no dissociation has happened. And when T equal to T equilibrium, at T equilibrium, let's say C alpha, let's say C alpha is dissociate, C alpha will dissociate same, so here C minus C alpha. So these things we have studied in dissociations whenever we are discussing about dissociations, on that we studied that how to write this. So from C alpha H means alpha H dissociate, so that is into C. Okay, so this we already discussed. After that, and we have the NaCN also, and this is completely dissociate into Na plus Cn minus. Okay, so let's say here given that we have the HCN H 0.2 molar, 0.2 concentrations. Okay, and you have the NaCl as also, let's say 0.2 molar concentrations. Okay, both have the 0.2 molar concentrations we are having with you. Okay, now let's say the key A, that is dissociation constant, or you can say that equilibrium constant, whatever. So for dissociation constant we are writing Kd. So any Kd is given for weak acids, that is how much, let's say 10 raised to minus 10. So why? Because with whenever we are having weak electrolytes and you are adding strong electrolytes with that, then the dissociation constant will decreases. That's why I written as 10 raised to minus 10. This is very low value. Okay, so how, so this value is comes when weak electrolytes added with strong electrolytes. Okay, so if you not add strong electrolyte, then how much Kd value is decreased, that we will look. Okay, so let's say so we know how to write equilibrium constant. So what is equilibrium constant? Equilibrium constant, or here the dissociation is happening, so I write Kd. So how to write? Concentration of product divided by concentration of reactant. So concentration of product is this, so C alpha, okay, sorry, C alpha divided by concentration of reactant, that is C minus C alpha. Okay, but thing is that here Cn minus has came to that solutions, with that in the solutions NaCN also present, means Cn minus also come, because in the solutions when we add the strong electrolytes in the water, that is completely dissociate. After that Na and Cn minus will behave independent, means they behave as only Cn minus. There is an Na plus attraction is there but very less, and Cn behave as independent, means here you cannot dissociate, you cannot like distinguish the Cn minus come from NaCN or HCN. So they will like look same and they give the same property. So in solutions we are having Cn minus this one also and this one also. It means when you are writing the dissociation constant, then you are writing that product divided by reactant, but in the reaction Cn minus cells also came. And we know that strong electrolytes, when you have given that whatever the concentration has given, that will completely dissociate. So if it is 0.2 molar, then it is also going to be 0.2 molar. This is also going to 0.2 molars, because strong electrolytes always dissociate completely, means whatever the concentration we are given, this equal amount will be dissociate. I mean, whenever you write NaCN or any strong electrolytes, this is going to give Na plus Cn minus. Okay, when T equal to 0, suppose we are given that 0.2 molar, no reaction happen, and whenever T equal to T equilibrium, this is completely dissociate, no NaCN will left. They are going to give it there 0.2 molar, 0.2 molar. Okay, so here that 0.2 molar of Cn minus is present with that, because Cn minus is completely dissociate, and in the solutions Cn minus also present, so we will write 0.2 molar also. Okay, because Cn minus comes from strong electrolytes also. Okay, and what do we know that for weak electrolytes, whenever you are writing the HCN, this is only partially dissociate, that is H plus Cn minus. That is, if you have the 0.2 molar, then from 0.2 molar only 5% will dissociate. That means that will be 5%, that is equal to nearly, if we say 5% of 0.2, means that value is very less value, like that value may be 0.005, something like that. You just calculate it. And so how much? 2 by 10 into pi by 100. So 10, 1000, that is your 0.01. So this is 0.01. So with compared to 0.2, 0.01 is very less value. So if you say 0.2, 0.01, then 0.021. So this value is very less with compared to, or 5%, or even less than 5% also. So that value dissociate very less. So whenever you say that 5% of that will dissociate, because this is weak electrolyte. So if we say T equal to 0, suppose this is 0.2 molar, then this is 0, and when you write T equal to T equilibrium, so this will be again it left as 0.0, sorry, 0.199, and it will be only 0.001 also. So very less it will dissociate. So what we say is that this C alpha value, this Cn minus value is very less compared to this value, so we just neglect this value. This tends to 0. So Kd equal to C alpha, and this value is very less compared to this value, so we keep it at 0. So this is into 0.2 molar, and here C minus, take common C 1 minus alpha, and this alpha values also, like C value is very less and alpha value also very less, because that is 0. That much of dissociate, and we are adding actual alpha value is 0.001, and whenever you are adding C alpha, then that become again less, because 0.2 into 0.001 0 1, so that value is become again very less, and this 0.1 value also, this the alpha value is 0.01, this value also very less. So if compared to 1, 0. This alpha value is very less, so we can take it as 1. So remaining is C alpha into 0.2 molar by C. So this C cancelled. So Kd equal to 0.2 molar alpha. So this is the value of Kd, and if you given that Kd is this much, okay, so if Kd is 10 raised to minus 10, then 0.2 molar alpha, and alpha has to come 10 raised to minus 10 divided by 0.2, that is 10 raised to minus 10, 2 into 10 raised to minus 1, that is 10 raised to minus 9 divided by 2. It right, you can write 10 raised to, that comes 5 into 10 raised to minus 8. So alpha value is, so whenever we give the weak electrolytes, if we add the strong electrolytes, then the alpha value is coming 5 into 10 raised to minus 8. So this amount of alpha means such a low dissociation is happening. So let's see, if you not add strong electrolytes, then what will be the dissociation constant value? With this alpha is dissociation constant, okay. So if you not add the strong electrolytes, so weak electrolytes we are having HCN, and this is dissociate into H plus Cn minus, okay, and let's say this is at t equal to 0, this is C value, so no dissociation happen, and when t equal to t equilibrium, let's say C minus alpha, C alpha and C alpha, okay, and let's say what is H? Okay, so we have not added any strong electrolytes now, okay. So if not added the strong electrolyte, then what is the dissociation constant value? Okay, that's what we are going to calculate. So Kd equal to, concentration of product divided by concentration of reactants. So that is C alpha, C alpha, C minus C alpha. So here, since we are not added any strong electrolyte, so only Cn minus is present in the solution. So this will be C alpha square, I can write C, and here C 1 minus alpha. So this cancel. So C alpha square 1 minus alpha, and since alpha value is very less, because this alpha value compared to 1 is very less, because this is strong weak electrolyte only 5% or less than 5% that is dissociate, so that value is very less. So Kd is equal to, this is nearly equal to 1, so C alpha square by 1, that is Kd equal to C alpha square. So alpha equal to Kd by C, this is square, so if alpha, then Kd by C root over, and since we have taken that HCN we are having 0.2 molars, and Kd we have taken 10 raised to minus 10. So concentrations we have taken 10 raised to Kd we have taken 10 raised to minus 10, and concentrations of HCNs we have taken 0.2 molars. So I will do 0.2 root So kd is 10 raised to minus 10, that is 2 into 10 raised to minus 1. Okay, so this alpha value has come 10 raised to 10 raised to that is 10 raised to minus 9 divided by 2 root over, so that will come how much, like you can write 10 raised to 10 raised to minus 8 2, so this is going to be 5. So alpha equal to 5 into 10 raised to minus 8 root over. So if you remove the root, then this is 5 is nearly root over of 5 into 10 raised to minus 4. So root 5 is value like root 4 is 2. So that is nearly 2, 2, 3 in between. So let's say it's 2.3 something approx we can take into 10 raised to minus 4. This is the alpha values when if you we are not taking the, if you're not adding the strong electrolytes. So if you add the strong electrolytes, then this is the alpha value, and if you not take the strong electrolytes, then alpha value comes 2.3 into 10 raised to minus 4. So it is seen that like whenever you are, this is what strong electrolytes plus weak electrolytes. Okay, this is only weak electrolytes. So whenever no strong electrolytes are added, then alpha value is 2.3 in 10 raised to minus 4. So very high value means whenever in the power if it is minus, then that is high value. Yes, so this value is like how much port like for to the power that time of high. So here this alpha value is 2.3 and 10 raised to minus 4, only weak electrolyte is there. Whenever you add in the strong electrolytes, then this is decreased into 5 into 10 raised to minus 8. So that amount of depressions in dissociations has happened when you are adding the strong electrolytes. Okay, so that is known as the common ion effect. So whenever you add, if you have the weak electrolytes, then that alpha value, the dissociation, it dissociate into H plus and Cn minus into this amount. And whenever you add the weak electrolytes, that will dissociate into this amount. So this value is decreasing. So if you add the strong electrolytes, this amount of dissociations. Dissociation means that H plus and Cn minus, that is dissociate. So that amount will decrease, means less amount of H plus and Cn minus will give if you add the strong electrolytes. Okay, so that is what I mean by common ion effect. So now next topic,